Today we're going to discuss the characteristics of functions. So what is a function? A function relates an input to an output. One way to think of a function is to think of it as a machine. We put stuff into the machine and it produces an output. If we put a certain input into our machine, we want to get one output. If we get more than one possible output from a single input, our machine is broken and hence it is not a function. Think of a machine that produces chocolate chip cookies. If we input the ingredients X, we should get chocolate cookies as our output Y. So our machine would be a function. We can even change X, the ingredients, and we should still get chocolate chip cookies since there is more than one recipe for making chocolate chip cookies. Now suppose there was a machine that when you input a particular set of ingredients X, sometimes you get chocolate chip cookies, but other times you get, let's say, pizza as your output Y. That machine would not be a function since you are getting two different outputs from the same input. Now, to define a function more formally, a function is a correspondence such that each member in the domain, which is our X values, corresponds to exactly one member in the range, our Y values. We say Y is a function of X. So with that said, a function has two special rules. One, it must work for every possible input value, and two, it has to have exactly one output for each input. Essentially, this states that one-to-many is not allowed. However, many-to-one is allowed for a function. So as I said before, the domain is the set of all possible inputs, which is our X values. And the range is the set of all possible outputs, our Y values. If a function is written in an equation in the form y equals f of x, then the domain of the function is all real numbers that can be substituted in for x to produce a real number for y. If a value of x is substituted that makes the function undefined, then that value must be excluded from the domain. And some of the ways a function can be undefined is if the substituted value of x produces division by 0, which we know we can't have, or the square root of a negative number, which we learned this semester is an imaginary number. Now, if you take a look at the picture on the right, we have a cubic function that's represented by a graph. To find the domain, we're going to go from left to right, and it's going to be all of our possible x values. When we're looking at our range, we're going to go from bottom to top, and we're going to find all our possible y values. As you go all the way to the left, the lowest possible x value is known as your lower bound. As you make your way to the right, you'll notice our x values are increasing. So as you continue along the x-axis, you'll find your highest possible x value. This is your upper bound. And you could repeat this process now for finding the range. This time I will start at the very bottom of the y-axis, and I'll look for my lowest possible y value. That will be my lower bound. And as I continue to work my way up the y-axis, I will increase my y values, and then eventually I'll find the highest y value, which is going to be my upper bound. Now, when you're going to write the domain and range of a function, you're going to use interval notation. Recall, interval notation uses both brackets or parentheses, dependent upon if the lower bound and upper bound values are included in the function. Now, let's take a look at a few examples for finding the domain and range of each function. So in this first graph, to find my domain, I'm going to go all the way to the left on the x-axis, and I'm going to continue moving to the right until I hit my first x value. And you can see here our first x value is at x equals 3. Now notice it's an open circle, so it's not included. So I'm going to say that my domain starts at 3, but it's not including 3. And as I continue to move to the right along the x-axis, I see that my last x value, which is my upper bound, has an x value of 4, and that point is included. And then to find my range, I'm going to start at the very bottom on the y-axis and work my way up until I hit my first y value. This will be my lower bound. So my first y value is at -4, and that's included. And as I continue to work my way up the y-axis, I can see that my highest upper bound y value is at y is 2, and we're not going to include that since it has an open circle. Now let's look at our second example. To find my domain, again, it's all my possible x values. So I'm going to start all the way on the left, and I see that my first x value is at x is -5, and it's not included. And as I work my way to the right, I can see that my next x value stops at x is -2, and it's included. And then it picks back up again at x is 1. So I'm going to put union, and 1 is included. And then I keep working my way to the right until I hit my last x value, which is at 5. And again, it's not included. Let's go ahead and look at our range. Our range goes from all the way to the bottom of the y values. That's at -1, -2, -3, -4. That's included. And as I work my way up, I can see that every x value is hit until I hit y is 4. Now, when we're finding x-intercepts, remember an x-intercept is the point in which the graph crosses the x-axis. To find this algebraically, you would set y equal to 0 and solve for x. There's many different names for x-intercepts, including roots as well as zeros. You can see here on the picture of the right, here are your two x-intercepts for this given graph. And then for y-intercepts, this is where the graph crosses the y-axis. And to solve that algebraically, we're going to set x equal to 0. And you can see again that this graph has one y-intercept. Let's go ahead and take a look at how to find the x and y-intercepts if they exist for each of the graphs below. So our x-intercept crosses the x-axis. So we see there's one x-intercept at 2, 0. And we have one y-intercept at 0, 4. And remember, those are just ordered pairs, so those get parentheses. And then in example 2, I have 3 x-intercepts. And the first one's at -2, 0. Next one's at our origin, 0, 0. And our final one is at 1, 0. In terms of our y-intercepts, the graph hits the y-axis and intersects it only once at the origin, 0, 0. So it's important to consider the different types of function behavior. Those 3 types include increasing, decreasing, and constant. When determining the type of behavior, you're always going to want to move left to right on the graph. In regards to increasing, this takes place when x gets bigger. You can see that my y values are also getting bigger. You can see here, this linear graph shows an increasing section because it has a positive slope. There is a direct relationship between x and y. As x gets bigger, so does y. With decreasing, as I move left to right, x is getting bigger, but my y values are getting smaller. They're decreasing. This is an inverse relationship. As x gets bigger, y gets smaller. One goes up, the other goes down. And then with constant behavior, that's when as x gets bigger, so as I move to the right, my x values are increasing, but my y values are simply staying the same. Now, when we're identifying the intervals of behavior for increasing and decreasing, again, we're going to use interval notation, which includes brackets and parentheses. However, because this is looking at increasing and decreasing, we're always going to use parentheses. And the reason for that is at one point, it could be increasing or it could be decreasing, depending on which side of the point you look at. So for simplicity, we're always going to use parentheses for intervals of increasing and decreasing. The interval measures the x values. The type of behavior describes the y values. Let's go ahead and take a look at an example. It says here we are given a graph. It says identify the intervals of behavior. So for increasing, you can see here at the very left, we have this section of the graph. From left to right, my x values are increasing and so are my y values. So this would be increasing. So we'll say from x is -1, -2, -4, to x is -2, that interval or part of the graph is increasing. Now, if you look at your next part of the graph, we can see here that from left to right, as x gets bigger, my y value stays the same. So that is a constant interval. So we would say the constant interval goes from -2 to +1. Again, we're going to use parentheses. And then for the last part of my graph, we have from left to right, this part of the graph is increasing since as x gets bigger, so does y. So we'll put union and we'll say x is 1 and it goes to x is 4. So you can write here that there is no parts of my graph, no intervals that are decreasing. So let's look at a second example. From left to right, I can see here that the first part of my graph, as x gets bigger, the y values are getting smaller. So there's that inverse relationship. As one goes up, the other goes down, so that part is decreasing. And we'll say that's from -2 to -1. Now the next part of my graph, from left to right, the x values are getting bigger, so are the y values, so that part is increasing. So we'll say that's from -1 to 0. And then the next part of my graph, as x gets bigger, my y values are getting smaller, so that part of the interval is decreasing from 0 to 1. So we'll put union 0 to 1. And then the last part of my graph, we can see that the x values are getting bigger, and so are the y values, so that last part is increasing. So we'll put union from 1 to 2. Now, if these graphs had arrows on it, like especially this last part, we would say that it would go from 1 to infinity. However, it stops at 2. And there was no intervals in this particular graph that were constant. So we'll just write none. Now, we've talked about maximums and minimums before in our quadratics unit. Remember, a minimum is the lowest point on your graph. A maximum is the highest point on your graph. So remember, when a parabola opened down, we had a maximum. When it opened up, we had a minimum. Those maximums and minimums are called absolute max and mins because it's the actual absolute highest or lowest point of our graph. Now, relative max and relative mins are slightly different. That relative word means simply that it's the smallest or highest point in that specific region. So anytime you see any peaks or hills in your graph, you know that's going to represent a relative maximum point. If you see any valleys in your graph, those represent minimum points. So you can see here in this graph below, it says what are the relative maximums and minimums for this graph. So for maximums, I'm going to just use a color here to represent those peaks or hills. Here is a relative max, and here is a relative max. And then our relative mins are our valleys. So here's a relative min, and here's another relative min. Now, in regards to end behavior, the end behavior of a graph describes the very far left as well as the very far right portions of the graph. To determine the end behavior, we're going to refer to the direction of the arrows and how they're pointed at both ends of the graph. Here's how we write end behavior. We're looking at it from both the left and right side. This first statement says for looking at the left end behavior of our graph, we're going to write it as x approaches -infinity. My function f of x is approaching, and that's where we'll take a look at where the y values are heading by looking at the arrow and which way it's pointed. And then we'll do the same thing for the very right side and look at the end behavior of that part of the graph by writing as x approaches +infinity, my function f of x approaches. Now, if you see here in the table below, here's a few examples. In this first example, we have a parabola that opens up. The left end behavior, so as I move left, I can see that my arrow is pointing up towards +infinity because the graph is rising. As I look at the right side end behavior, so as x gets bigger, I can see my arrow's pointing up again, so it's +infinity that it's approaching. In example 2, we can see that as x gets smaller, so as I go further and further left, I can see my y values are getting smaller as well because they're going down towards -infinity. As I go further and further right, my y values are decreasing, and it's again going towards -infinity. In my third example, as I go further and further left, my arrow's pointing down towards -infinity. As I go further and further right, my arrow's pointing up towards +infinity. And then lastly, in this fourth example, as I go further and further left, I can see my arrow's pointing up towards +infinity. And as I go further and further right, my arrow's pointing down towards -infinity. And the last thing that we're going to look at is starting to identify the different types of functions that we'll be talking about in this class. We've already discussed quadratic functions. Remember, a quadratic function takes the form y = ax² + bx + c, and its graph is a parabola. We already looked at the square root function. Remember, square root function has a radical sign inside the function, and the graph starts at an endpoint and continues in a curve in one direction. An absolute value function has the absolute value symbols in it, and it takes a V shape. The two new functions that we're discussing in this unit are going to be greatest integer function, and we'll spend the next day or two talking about how to graph these. If you look here, you can see a greatest integer function is called a step function because the graph looks like a bunch of steps. And then the last one is a rational function. We've talked about rational functions. Remember, a rational function is a ratio of polynomials in both the numerator and denominator. And we can graph these, and we'll identify a few points of discontinuities, which are called holes and asymptotes. Again, we'll be talking about greatest integer function and rational function in the next few days.